Janus-Pro, Unified Multimodal Understanding and Generation with Data and Model Scaling by Xiaokang Chen, Zhuyu Wu, Qing Chao Lui, Zizeng Pan, Wen Lui, Zinda Zi, Xingqiai Yu, Chong Ron, DeepSeek AI. Abstract. In this work, we introduce Janus-Pro, an advanced version of the previous work, Janus. Specifically, Janus-Pro incorporates 1. An optimized training strategy, 2. Expanded training data, and 3. Scaling to larger model size. With these improvements, Janus-Pro achieves significant advancements in both multimodal understanding and text-to-image instruction following capabilities, while also enhancing the stability of text-to-image generation. We hope this work will inspire further exploration in the field. Code and models are publicly available. Introduction. Recent advancements in unified multimodal understanding and generation models have demonstrated significant progress. These approaches have been proven to enhance the instruction following capabilities in visual generation tasks while reducing model redundancy. Most of these methods utilize the same visual encoder to process inputs for both multimodal understanding and generation tasks. Since the representations required for these two tasks differ, this often results in suboptimal performance in multimodal understanding. To address this issue, Janus proposes decoupling visual encoding, which alleviates the conflict between multimodal understanding and generation tasks, achieving excellent performance in both tasks. As a pioneering model, Janus is validated at the 1 billion parameter scale. However, due to limited amounts of training data and the relatively small model capacity, it exhibits certain shortcomings, such as suboptimal performance on short prompts, image generation, and unstable text-to-image generation quality. In this paper, we introduced Janus-Pro, an enhanced version of Janus that incorporates improvements across 3 dimensions: training strategies, data, and model size. The Janus-Pro series includes 2 model sizes, 1 billion and 7 billion, demonstrating scalability of the visual encoding-decoding method. We evaluate Janus-Pro on multiple benchmarks, and the results reveal its superior multimodal understanding capabilities and significantly improved text-to-image instruction following performance. Specifically, Janus-Pro 7 billion parameter achieved a score of 79.2 on the Multimodal Understanding Benchmark, MMBench, surpassing state-of-the-art unified multimodal models such as Janus, TokenFlow, and Metamorph. Additionally, in the text-to-image instruction following leaderboard, GenEval, Janus-Pro 7 billion scores 0.80, outperforming Janus, DALL-E 3, and Stable Diffusion 3 medium. Method. The architecture of Janus-Pro is shown in Figure 3, which is the same as Janus. The core design principle of the overall architecture is to decouple visual encoding for multimodal understanding and generation. We apply independent encoding methods to convert the raw inputs into features, which are then processed by a unified autoregressive transformer. For multimodal understanding, we use the SIG-LIP encoder to extract high-dimensional semantic features from images. These features are flattened from a 2D grid into a 1D sequence, and an understanding adapter is used to map these image features into the input space of the LLM. For visual generation tasks, we use the VQ tokenizer from the following link to convert images into discrete IDs. After the ID sequence is flattened into 1 dimension, we use a generation adapter to map the code block embeddings corresponding to each ID into the input space of the LLM. We then concatenate these feature sequences to form a multimodal feature sequence, which is subsequently fed into the LLM for processing. Apart from the built-in prediction head in the LLM, we also utilize a randomly initialized prediction head for image predictions in the visual generation task. The entire model adheres to an autoregressive framework. Optimized training strategy. The previous version of Janus employs a three-stage training process. Stage 1 focuses on training the adapters and the image head. Stage 2 handles unified pre-training, during which all components except the understanding encoder and the generation encoder has their parameters updated. Stage 3 is supervised fine-tuning, building upon Stage 2 by further unlocking the parameters of the understanding encoder during training. This training strategy has certain issues. In Stage 2, Janus divides the training for text-to-image capabilities into two parts following PixArt. The first part trains on ImageNet data using image category names as prompts for text-to-image generation, with the goal of modeling pixel dependence. The second part trains on normal text-to-image data. During implementation, 66.67% of the text-to-image training steps in Stage 2 are allocated to the first part. However, through further experimentation, we find that this strategy is suboptimal and leads to significant computational inefficiency. To address this issue, we make two modifications. Longer training in Stage 1, we increase the training steps in Stage 1, allowing sufficient training on the ImageNet dataset. Our findings reveal that even with the LLM parameters fixed, the model could effectively model pixel dependence and generate reasonable images based on category names. Focus training in Stage 2. In Stage 2, we drop ImageNet data and directly utilize normal text-to-image data to train the model to generate images based on dense descriptions. This redesigned approach enables Stage 2 to utilize the text-to-image data more efficiently, resulting in improved training efficiency and overall performance. We also adjust the data ratio in Stage 3 supervised fine-tuning process across different types of datasets, changing the proportion of multimodal data, pure text data, and text-to-image data from 7 to 3 to 10 to 5 to 1 to 4. By slightly reducing the proportion of text-to-image data, we observe that this adjustment allows us to maintain strong visual generation capabilities while achieving improved multimodal understanding performance. Data scaling. We scale up the training data used for Janus in both multimodal understanding and visual generation aspects. Multimodal understanding. For the Stage 2 pre-training data, we refer to DeepSeek VL2 and add approximately 90 million samples. These include image caption datasets, as well as data for table, chart, and document understanding. For the Stage 3 supervised fine-tuning data, we also incorporate additional datasets from DeepSeek VL2, such as meme understanding, Chinese conversational data, and datasets aimed at enhancing dialogue experiments. These additions significantly expanded the model's capabilities, enriching its ability to handle diverse tasks while improving the overall conversational experience. Visual generation. We observe that the real-world data used in the previous version of Janus lacks quality and contains significant noise, which often leads to instability in text-to-image generation, resulting in aesthetically poor outputs. In Janus-Pro, we incorporate approximately 72 million samples of synthetic aesthetic data, bringing the ratio of real to synthetic data to 1:1 during the unified pre-training stage. The prompts for these synthetic data samples are publicly available, such as those in the following link. Experiments demonstrate that the model converges faster when trained on synthetic data, and the resulting text-to-image outputs are not only more stable, but also exhibit significantly improved aesthetic quality. Model scaling. The previous version of Janus validates the effectiveness of visual encoding and decoupling using a 1.5 billion parameter LLM. In Janus-Pro, we scale the model up to 7 billion parameters, with the hyperparameters of both the 1.5 billion and 7 billion parameter LLMs detailed in Table 1. We observed that when utilizing a larger scale LLM, the convergent speed of losses for both multimodal understanding and visual generation improved significantly compared to the smaller model. This finding further validates the strong scalability of this approach. Experiments. Implementation details. In our experiments, we utilized DeepSeek LLM 1.5 billion and 7 billion with a maximum supported sequence length of 4096 as the base language model. For the vision encoder used in understanding tasks, we select SIG LIP large patch 16384. The generation encoder has a codebook of size 16,384 and downsamples images by a factor of 16. Both the understanding adapter and the generation adapter are two-layer MLPs. The detailed hyperparameters for each stage are provided in Table 2. Please note that for Stage 2, we employ an early stopping strategy, halting at 270,000 steps. All images are resized to 384 by 384 pixels. For multimodal understanding data, we resize the long side of the image and pad the short side with the background color to reach 384. For visual generation data, the short side is resized to 384 and the long side is cropped to 384. We use sequence packing during training to improve training efficiency. We mix all data types according to the specified ratios in a single training step. Our Janus-Pro is trained and evaluated using HAI LLM, which is a lightweight and efficient distributed training framework built on top of PyTorch. The whole training process took about 9 to 14 days on a cluster of 1632 nodes for 1.5 billion, 7 billion parameter model, each equipped with 8 NVIDIA A100 40GB GPUs. Evaluation setup. Multimodal understanding. To assess multimodal understanding capabilities, we evaluate our model on widely recognized image-based vision language benchmarks, which include GQA, POPE, MME, SEED, MMB, MMVET, and MMMU. Visual generation. For evaluating visual generation capabilities, we use GenEval and DPG-Bench. GenEval is a challenging benchmark for text-to-image generation designed to reflect the comprehensive generative abilities of visual generation models by offering a detailed instance-level analysis of their compositional capabilities. DPG-Bench, Dense Prompt Graph Benchmark, is a comprehensive dataset consisting of 1,065 lengthy, dense prompts designed to assess the intricate semantic alignment capabilities of text-to-image models. Comparison with state-of-the-arts. Multimodal understanding performance. We compare the proposed method with state-of-the-art unified models and understanding-only models in Table 3. Janus-Pro achieves the overall best results. This can be attributed to decoupling the visual encoding for multimodal understanding and generation, mitigating the conflict between these two tasks. When compared to models with significantly larger sizes, Janus-Pro remains highly competitive. For instance, Janus-Pro 7 billion parameter outperforms TokenFlow XL, which is 13 billion parameters, on all benchmarks except GQA. Visual generation performance. We report visual generation performance on GenEval and DPG-Bench. As shown in Table 4, our Janus-Pro 7 billion parameter obtains 80% overall accuracy on GenEval, which outperforms all the other unified or generation-only methods, for example, transfusion, SD3 medium, and DAL-E3. This demonstrates that our approach has better instruction following capabilities. As shown in Table 5, Janus-Pro achieves a score of 84.19 on DPG-Bench, surpassing all other methods. This demonstrates that Janus-Pro excels in following dense instructions for text-to-image generation. Qualitative results. We present the results on multimodal understanding in Figure 4. Janus-Pro exhibits impressive comprehension abilities when handling inputs from various contexts, showcasing its powerful capabilities. We also present some text-to-image generation results in the lower part of Figure 4. The images generated by Janus-Pro 7 billion are highly realistic, and despite having a resolution of only 384 by 384, they still contain a lot of details. For imaginative and creative scenes, Janus-Pro 7 billion parameter accurately captures the semantic information from the prompts, producing well-reasoned and coherent images. Conclusion. This paper introduces improvements to Janus from three aspects: training strategy, data, and model size. These enhancements have led to significant advancements in both multimodal understanding and text-to-image instruction following capabilities. However, Janus-Pro still has certain limitations. In terms of multimodal understanding, the input resolution is limited to 384 by 384, which affects its performance in fine-grained tasks such as OCR. For text-to-image generation, the low resolution combined with reconstruction losses introduced by the vision tokenizer results in images that, while rich in semantic content, still lack fine details. For example, small facial regions occupying limited image space may appear under-detailed. Increasing the image resolution could mitigate these issues. My summary. Janus-Pro builds on the original Janus framework to unify multimodal understanding and text-to-image generation tasks by decoupling their visual encoders. It improves upon Janus with a more efficient training strategy, larger, higher quality multimodal datasets, and a scaled model size up to 7 billion parameters. These refinements significantly boost performance on multimodal benchmarks like GQA, POPE, MMBench, and also text-to-image instruction following tasks like GenEval, DPG-Bench, producing more stable and detailed images.